Hi, everybody. Let's start by getting out your pendulum introduction worksheet that I gave to you yesterday with the picture of the pendulums on the back. If you don't have that, there is a folder at the front of the room called Physics Handouts where you can find some more. So once you have that out, we're going to be taking notes on that as on the back side like we did yesterday as we're taking notes in class. Now, every class is in a slightly different position. So if you're like, hey, she talked about that yesterday, no big deal. Why don't you flip it over and work on the problems on the front side that you can, because the front side is going to be homework tonight. Okay, so here we are. I'm going to do a recap of kinetic energy. Everybody got through this yesterday, but I just wanted to make sure that we all had this. So when we're talking about a pendulum, we have kinetic energy. We're going to talk about the max and the min. So for a spring or a pendulum, kinetic energy is 1/2 mv squared, like it always has been. And then when the speed is maximum, so is the kinetic energy, right? This makes sense because kinetic energy has speed as a component and the mass is not changing. So what affects the kinetic energy is the speed. When the speed is minimum, so is the kinetic energy. Okay, but not everyone got to potential energy. So let's talk about potential energy for a second. So if you think about a swing, you can think about where you have the most potential. And just like we did problems where you're at the top of a slide, you have the most potential energy when you're furthest from the ground. So potential energy max and min, let's talk about that. For a spring, we're going to use the same equation that we had for elastic potential energy. So that's 1/2 kx squared. And just as a refresher, because it's been a bit since we looked at this equation, the k is your spring constant, which you'll always be given or you're solving for, but it's a spring constant. It's unique to each spring, and it tells you how willing that spring is to move, essentially. And then X is how much that spring compresses or is stretched from its resting position. So again, X is that maximum stretching point or the maximum compression point of the spring. For a pendulum, again, think about a swing on a swing set. This one's straightforward. It's just gravity, right? So your potential energy is mgh. So let's talk about max and min. So when the displacement is maximum, like when you're furthest from that equilibrium point. So if you're swinging on a swing, when you're the highest up you can possibly be, right? The displacement is at its maximum. H if it's a pendulum, X if it's a spring. So is the potential energy. You can think about this with a spring as well. If I'm stretching the spring as far as it'll go, it has tons of potential energy. So when I let go, it's just going to transfer to kinetic. When the displacement is minimum, again, when your X or your H is minimum. So when you're really close to the ground, if you're on a if you're on a swing, or when it's in its relaxed state of the spring, the potential energy is also at a minimum. This makes sense because you would have your highest kinetic energy there. So let's pause for a second and go back to your pendulum introduction sheet on the back and the pendulum. So it says the point of maximum kinetic energy. So where is this thing moving the fastest? So when you're swinging on a swing set, you're fastest at that equilibrium point. So that would be B. The point of maximum potential energy, this is where you have a zero velocity. This would be your highest point in either direction. So this is points A and C. Okay. Okay, so some of you left off at restoring force. So restoring force is, we talked about this in the definition of simple harmonic motion. I said we were coming back to it. Now is that time. So the definition that restoring force is the force that pulls the mass back to the equilibrium position. So the restoring force is the force that pulls the mass back to the equilibrium position. So this is the force that it takes to bring it back to that set position. Now this was listed in the simple harmonic motion definition. The restoring force is directly proportional to the displacement of the mass from the equilibrium position. What in the world does that mean? Now that we know what restoring force means, we can talk about this. Directly proportional just means when something goes up, the other thing goes up. So we're saying that restoring force, when restoring force goes up, or essentially restoring force will go up when displacement goes up. So in other words, if I'm really far away from the equilibrium point, then I'm going to need a really big force to get me back. If I am really close, if I have a small displacement, I'm going to need a small force to bring me back. Right? So that's what that big sentence means. Now we know that force equals mass times acceleration. So when the restoring force is at a maximum, so is the acceleration. Now that is kind of tricky to think about, because if we think about this, our restoring force is going to be the largest the furthest I am away from the equilibrium. Well, if you're on a swing, that's like as high as you can get. And we all remember that fun hang time there. We're not actually, our velocity is 0 for a second. You're just like not moving in the middle of the air, and then you swing back. Right? So you're saying, Michaud, the acceleration is greatest when the velocity is 0? Yeah, instantaneous velocity is 0, but acceleration is change in velocity. And we're going from a negative velocity to a positive, or from a positive to a negative, and that change is great. And because of that, our acceleration is greatest when I'm furthest away. So let's do the max. At max displacement, the restoring force is at a maximum. At a maximum displacement, the restoring force is at a maximum. Okay, this makes sense. If I'm far away, it takes a big force to get back. And at the minimum displacement, the restoring force is a minimum. This makes sense. I'm not really far away, so I have a small force. Okay, so let's go ahead and look at your pendulum introduction sheet. Now, everyone should be here. All the classes should be here. So if you've been distracted, come on back. So we're at your pendulum introduction sheet on the back side. All right, so where's the restoring force at a maximum? So we're starting at G, right? Restoring force is at a maximum. That would be when it's furthest away, so that's points A and C. H, when is acceleration at a maximum? Again, that's whenever the force is at a maximum, so A and C. I, where is restoring force at a minimum? That's going to be when it's closest to equilibrium, because that's a really tiny force to bring it back to equilibrium. So I is going to be B. And then J, acceleration is at a minimum. Where is that? That is at point B. Okay, so we are done with that. And we've got one more concept to talk about before I move on, and that is the concept of damping. When you were swinging the pendulum back and forth, a couple of you said when you were making your pendulums, you're like, Michaud, but it doesn't come all the way back. You're right, it doesn't. So in an ideal system, the simple harmonic motion would continue indefinitely. Well, that's a perpetual motion machine. We can't actually make them, right? That's not real life. Why is it not real life? Because in real life, we have things like friction. So in the real world, friction slows things down and eventually stops the motion. So in the real world, you have friction with the rope on the top of the rod that you guys had to make your pendulums yesterday. And in the real world, eventually that rope is rubbing on the rod and it is going to cause friction, which slows it down as it goes. And the effect of slowing down until it gets back to equilibrium is called damping. Now, it just doesn't go there and stop. We saw that it slows and slows and slows and doesn't quite reach its displacement each time and gets a little bit shorter and shorter and shorter until we're at equilibrium. So it's something like this, right? So you have the displacement. You have this thing here where it goes, like, if this is the swing of your pendulum, let's say, we go up to the top and then it swings this way, but then it swings here a little bit less, 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 blah. So this is what damping is. Today we're going to talk about the specifics about how pendulums work, and then tomorrow we'll go on to springs. So we can't talk about pendulums without talking about the best example of this simple harmonic motion, which is the disastrous bridge collapse of the Tacoma Narrows Bridge, which people used to call Galloping Gertie, because when the winds would go through, the bridge would oscillate, move back and forth. Now, if you've seen this before, awesome. Now you get to see it again. So we're going to watch that. I know you're probably wondering what on earth were people doing on that bridge? And it was moving so much that scientists went to go to actually study it and film the motion. And they had no idea that the bridge was going to collapse until obviously the motion started amplifying. And we'll talk more about how that happened as we get later when we start talking about waves. Okay, so this is a little bit of a refresher about period. So period, which we've talked about before, is the time it takes one complete cycle to go over and back again. So it's the time it takes one complete cycle to go over and back again. So again, we know this because you made a pendulum and you had it go for a certain period, but I thought we would just refresh all the things since, it's been a bit. The units for a period are time in seconds. Okay, and we tend to talk about this. Every now and then people refer to frequency, but most of the time in the equations we're going to use, we're going to talk about period. So if this is what you already know and you don't need to write it down, awesome. Frequency is the next thing. So again, frequency is the number of complete cycles or vibrations, in this case the up and back, per unit of time. So I'm not sure we really talked about last time we talked about frequencies. This part is new, is the SI unit for frequency is seconds to the -1. And that's actually how they write it instead of 1 over S, but I'd also take 1 over S. But the term is actually a hertz. So HZ is how it's abbreviated. And you'll remember that period and frequency are reciprocals of each other. So period equals 1 over the frequency, and frequency equals 1 over the period. So these are all equations that you've had before. So now that we've refreshed what period and frequency are, and now that we have terms for frequency, or units for frequency, let's get into specifics about how a pendulum works. Okay, so let's talk about how we calculate the period of a pendulum. You all noticed when you built your pendulum that the length mattered, and that is really the big factor in the pendulum. So the period of a pendulum depends on the length of the pendulum. So the amount of time it takes to go back and forth really depends on how long that pendulum is. And here is the equation. It's on your equation sheet, but we're going to write it down. I know it might be a little bit hard to see in the back. So T equals 2 pi times the square root of L over A sub G. Okay, so T equals 2 pi times the square root of L divided by A sub G. And just to remember, T is the period, L is the length of the pendulum, and A sub G is the acceleration due to gravity. So T is the period, L is the length, A sub G we know is gravity. Notice, what do you not see in here? Mass. That's because it doesn't matter. The mass of the pendulum does not affect the pendulum speed. I could make that mass super heavy. It does not matter. Length is what matters for the pendulum. Okay, so I know you might need a second to write this down still. We are going to do some examples, and I'm going to read through the examples and then we'll do them, and then we can do them together. But I want you to try the examples as I'm working them as well. So here's our first example. What is the period of a 3.98 meter long pendulum? Okay, I don't have a whole lot of room, so I'm going to write it kind of squished, but we'll be okay. So given, I have my length is 3.98 meters. And the unknown is t. And I'm going to put my equation over here. My equation is the same one we just wrote down, 2 pi, or t equals 2 pi over square root of L over A sub G. Okay, so let's solve that. So we don't know what t is, so t equals 2 times pi over square root of 3.98 divided by 9.8. Right, now we're going to be doing things with square roots and solving for things under square roots, and I know this is not our favorite. So I want you to practice this on your TI-84s. If you need to get up and borrow one of my TI-84s, go for it. But I want you to try this. So take a second, grab an 84, try this on your calculator. Okay, at this point, I'm assuming you have your 84. If not, you're on your way to getting your 84 out. Okay, and why don't you go ahead and try this right now. So 2 pi times the square root of 3.98 divided by 9.8. Again, you're going to have to be careful how you do parentheses under the square root. Okay, I got this with 2 sig figs, 4 seconds. So I want you to check and make sure that you can do this on your calculator, that you can get 4. Okay, the next question says, hey, what's the frequency? So we know that frequency is just 1 over t. So that's what we're going to do. We're going to go 1 over 4. That's really nice. I don't even need to do that on my calculator. And then my units are hertz. Okay, so there's our first example. Now, if you didn't get a chance to do this one on your calculator, that's fine, but the next you really need to do on your calculator. Okay, this one. A desktop toy pendulum swings back and forth once every 1 second. How long is the pendulum? Okay, so given what I have here is it goes back and forth every 1 second. So they're telling me that's my period. Sometimes if I get lost, I look at the units, right? Seconds. That tells me it's not in seconds to the -1 or hertz, so I know it's not frequency, it has to be period. So, okay, I want to know what L is, and my equation, T equals 2 pi times square root of L A sub G. Fine. All right, so, okay, I know what period is, 1.0, and I have 2 pi over L 9.8. Okay, we're going to algebra here. I have to solve for something under a square root. So what I'm going to do first is divide both sides by 2 pi so that I can cancel out 2 pi. What I'm left with is 1 over 2 pi equals square root of L over 9.8. Now think to yourself for a second, how do I do this? What's the next step? Oh, did yourself say the next step is to get rid of the square root by squaring both sides? Because that's correct. Okay, so now I have 1 over 2 pi, whole thing squared, equals L divided by 9.8. Well, okay, I can multiply both sides by 9.8, and that'll get rid of my 9.8. So L is equal to 9.8 times 1.0 over 2 pi. So that was some algebra. Please take a second and try this on your calculator. Make sure you can get this on your calculator. And again, I'm not here today, but I'll be around the other days. And by all means, if you are having difficulty with the algebra, please come by homeroom. I would love to show you how it works. Okay. When I did this, and I checked my math a couple of times, so I hope I'm right, but I got this with sig figs. Okay, so that's where we're at there. All right, couple more to go. We got this. Okay, let's read this one. So we have, what's the acceleration due to gravity at a location where a 6.00 meter long pendulum swings through exactly 100 cycles in 492 seconds? Okay. Oh, this one's a doozy. Why is it a doozy? Because I don't actually have period. I have period. Period is in how many seconds it takes to do one cycle, but I have 100 cycles. So that's the first thing I've got to solve for. I know that it takes 492 seconds to go 100 cycles. So, okay, fine. That is, in one cycle, that would be 4.92 seconds. So that's the first tricky aspect. The next tricky aspect is what I'm solving for, acceleration due to gravity. She's not pretty because she is under a square root in the denominator. Right? So I got to solve for this shenanigans. Tricky. All right, so step one. I'm going to say 492 seconds. My other given, by the way, was length of 6.00 meters. So this equals 2 pi times 6 over a sub g. All right, let's let this go right here. First thing I'm going to do is divide both sides by 2 pi. So I'm left with 4.92 divided by 2 pi equals square root of 6 over a sub g. We're going to do exactly what we did in the problem before. We're going to square it. 4.92 squared over, or 4.92 over 2 pi whole thing squared equals 6 over a g. Okay, now I need to get a g. I need to get it out of the denominator. So I'm going to multiply both sides by a sub g. That's a q. A sub g and a sub g. So what I have here is a sub g times 4.92 over 2 pi squared equals 6, because these would cancel out. All right, great. Now I got to divide both sides by 4.92 over 2 pi squared. Wonderful. I'm going to simplify this and say it's 6 divided by, because these would cancel out, and this would be 4.92 over 2 pi squared. So I'm going to say 6 divided by, and I think if you'll remember, I can distribute this to both sides. So I'm going to say 4.92 squared over 2 pi squared. Okay, this is some serious algebra. Keep, change, flip. Okay, there's all the algebra I need to do to get to my answer. Now, if you're like, oh, Miss Shope, that is too much algebra for me, fine. I might do this a little bit differently. I'm going to erase this original given, the unknown, the equation for bit, and I'm going to rewrite it in a different way. Okay, so I'm going to leave this last part up so you can see all the fun algebra that I did. And if you love algebra, you're like, sweet, this is awesome. And if you don't, you're like, no. So if I am not a big fan of the algebra, what I might do is starting at this equation. So we had 4.92 equals 2 pi times 6 over a sub g. So I know that I need to divide both sides by 2 pi. So I'm going to do that. And then if I don't like the fraction algebra, I might just do the math for this. And if I go 4.92 divided by 2 pi, I get 0.783. And that might be a lot easier for you to see this problem so you don't look at that craziness, right? Then we could square both sides. And then we would get 0.783 squared over 6 equals 6 over a sub g. Then I would just have to go, okay, a sub g equals 6 divided by 0.783 squared. And that might be easier to even just see. Either way, when I do that, I get the acceleration due to gravity as 9.8 because I need 2 sig figs, but my answer that I got was 9.7865 something something. But I need 2 sig figs, so here we go. Why 2? Because 1 equals 2 in sig figs. Okay, that was a tricky one. So making sure you know how to do the crazy algebra for this. Again, I am around during homeroom, so if you want to come by on a day that I'm there, come by during homeroom and I can help you with the algebra. One more to go. You got this. Okay, our last problem is a proportional reasoning problem. I know. So the acceleration due to gravity on planet Zuzu is approximately 1/9 of the acceleration of gravity on the Earth. How would the period of the pendulum on planet Zuzu compare with the period of the same pendulum on the Earth? Okay, so essentially what we're saying is on Zuzu, it's 1/9 times a sub g. So, okay, proportional reasoning. What I'm going to do is say 2 pi L, and then here I'm going to say instead of a sub g, I'm multiplying 1/9 times a sub g. Okay, denominators trip me up, so I'm going to rewrite this in another way. I'm going to say that's the same thing as saying 1 over 1/9 times L over a sub g. Okay, 1 divided by 1/9. 1 divided by 1/9. Keep, change, flip. That's just 9. So, okay, that's reasonable. What I'm saying now is the period equals 2 pi times the square root of 9 times L over a sub g. And we know that the square root of 9 is 3, so the period is 2 pi 3 times, right, square root of L over a sub g. So if I do something to one side, I must do it to the other. So the period is 3 times greater on planet Zuzu. Again, if proportional reasoning is tricky, come and chat with me during homeroom. Okay, your homework tonight is to do the first side of the pendulum introduction sheet. So if you haven't already, please start working on that, and then I will check that tomorrow. Bye.